Welcome to our second topic in trigonometry. It is topic number 33 and it is called Sine and Cosine rule. The family of right-angled triangles have proven to be among the simplest mathematics devices to manipulate. It forms the basis of all concepts in trigonometry. We are about to address the triangles that are not right-angled, and we will see that right-angled triangles play a very important role if it is even in the initial stages. The properties of all triangles that simplify their uses and solutions I have described as cyclic and symmetrical. The understanding and use of the sine and cosine rule can be shown to depend on facts that are confirmed by simple logic. It is important that students realize that no matter how complicated a formula appears, it is dependent on the relationships between the sides and angles of a three-sided figure. The number of sides are not only finite, but it is a small number. Students should therefore expect no visible surprise from a phenomenon much simpler than a three-card trick. The sine rule is derived by finding the area of a triangle. The rule is applicable to all triangles, but it is only necessary when the triangle is not right-angled. To make life easy, the sides and angles of a triangle are named in a special way. This unifies the relationship between the sides and angles in the student's mind. So side A is opposite to angle A that we have right there, and we can see very clearly indicated. Side A is opposite to angle A, and what do you imagine? Side, which is represented by lowercase b, is opposite to the side that is represented by uppercase B. And no surprise, the side C is opposite to the angle C. There we have it. The area of a triangle is used to derive the sine rule. Area is equal to a half the product of the base and the height. So it's half base times height. So let us use the side A as the base. So side A will be our base. Good. When finding the area of a triangle, we may use any side as a base. Irrespective of the side that is used as a base, the height should be perpendicular to it. So the height is always perpendicular to the base. What does that cause? We need an expression for the height in terms of the sides and angles that are given. It is good that it is perpendicular to the base. It is good that the height is perpendicular to the base. Why? We therefore have two right-angled triangles. We have more than what we bargained for, because one right-angled triangle is always going to be good enough. So we have two this time, one on the left and the other on the right. That is the one that is on the left. That is the one that is on the right. The one that is on the right is not so much used. The one that is on the left is the one that we are going to be using to derive our relationship for the height. So the right angle triangle on the right will be neglected, and the one that is on the left is going to be used to derive an expression for the height. In the right angle triangle, the known quantities that are taken from the original triangle are the side B and the angle C. So we have it right down here. We have what comes from the original setting. We have B. That side B comes back right there, and that angle C goes back right there. And of course, the height is what we need to determine. B is the hypotenuse of the elemental right angle triangle. So B is the hypotenuse, the side that is opposite to the right angle. And the height that we have there is opposite to the angle C. So the angle C, we have it right there, and the height is opposite to it. That is the opposite. So of course we are looking now at opposite and hypotenuse. The trig ratio that applies is sine. No surprise, because we are deriving the sine rule. So the trig ratio that applies in this situation is sine, because we have opposite and we have hypotenuse, and we know that the trig ratio that deals with opposite and hypotenuse is sine. And of course, it shouldn't be surprising because we are really working with the sine rule. So sine c is equal to opposite over hypotenuse, and of course we're going to put in the opposite and we're going to put in the hypotenuse. So the opposite is the height and the hypotenuse is b. So let us see how we find height. Of course, it's just a matter of transposing simply. The height we have here and b is multiplied on the other side because we have it divided on this side, so it is multiplied on the other side. So b sine c is equal to the height, so the height is equal to b sine c. Now we have our new expression for the height, which is height is equal to b sine c. And let us see what the area is. So it is in reference to our original triangle, whose base is a and the height is indicated. So we know that the base is a. So write down the formula for the area of a triangle. It is half base times height. But do you know what the base is? The base is a. We have it right here. And what the height is? We found it right there to be b sine c. So base is equal to a and the height is equal to b sine c, as we have indicated a short while ago. So the base is a right there, and the height we note from here b sine c. So in where we have a half base times height, we are going to have a half a and then the height is b sine c. So we're going to have that replaced with area is equal to a half a times b sine c, or we may write it as a half ab sine c. Right, so area is equal to a half AB sine C. And we have a lovely question here. Is there a pattern? And the answer is sure there is. All formulae that pertain to triangles are based on simple patterns. The area of any triangle can be found by taking half of the product of any two sides and multiplying the result by the sine of the angle that the two sides form. So we're going to take half of the product of any two sides. So any two sides of the triangle that you may want to use, you may. But you have to multiply that by sine of the angle that the two sides form. So here we have an examination of the sine rule. So examine the formula against the geography of the triangle, taking note of the positions of the sides and angles involved relative to each other. So we have area is equal to a half AB sine C. And what do you know? AB, take note of the positions of the two sides that are in the formula. And, of course, take note also that the angle in the formula is formed by the two sides that are in the formula. So use any two sides and use the angle that the two sides form. In addition to our earlier statement, we may say that the formula for the area of a triangle is defined on any vertex, that is, the angle and two sides involved in the vertex. So, as long as you are working with the area of any triangle at all, it can be found by focusing on a single vertex. So you go to the vertex, look at the two sides that form the vertex, and also look at the angle that the two sides form. We are going to use that same pattern to derive another formula, and we are going to be using another vertex. When we use the vertex, we have to use the two sides that form the vertex, and of course the angle involved. The two sides that form the angle are B and C, as you can see. And there you are taking a look also. The angle A is the one formed by the two sides B and C. So, what do we have then? The two sides will therefore have their positions in the formula. So these two sides that we have there, B and C, are going to be in the formula, and the angle that the two sides form are also going to be inside the formula. So we have area is equal to half BC sine A. The angular representative of the vertex will also be in the formula, no problem with that. That is already established and stated. In addition to our earlier statement, we may say that the formula for the area of a triangle is defined on any vertex, that is, the angle and the two sides involved in the vertex. Here we have another vertex, and we are going to define, or we are going to express the area of the triangle based on the information at the vertex. The vertex that we are going to be using is the one at angle B. The angle involved is B. The formula of the area on the vertex of the triangle can therefore be written down without much ado about anything. So we have the formula here can be written down, and we're going to have half of AC sine B. So A and C are the two sides that form the vertex, and B is the angle in the vertex. So that is how we always define formula for the area of a triangle. The formulae that were derived all accurately give the area of the triangle. Therefore, they are equal. So, because the three formulae that we use, remember them? Half BC sine A, half AC sine B, half AB sine C. Because they all accurately give the area of the triangle, they are all equal. So this is the basis of our sine rule. Now we are going to derive this sine rule. We are going to remove the halves from the formula by multiplying the entire equation by 2. We are going to remove the halves from the formula, and that is done by multiplying the entire equation by 2. So let's do that. So we're going to see that 2 multiplied by a half is going to be equal to 1. So 2 multiplied by a half means 2 over 1 multiplied by 1 over 2. And these two will cancel, and the answer is equal to 1 over 1, which is 1. But we do not need to write 1 as the coefficient. 1 as a coefficient is not necessary. 1 is usually the default coefficient, so the formula can be written just as we have it right there. BC sine A is equal to AC sine B is equal to AB sine C. Next, let us divide each term by ABC. So these are the terms, BC sine A, AC sine B, all of those terms will be divided by ABC. Let us see what happens. In the first fraction, we have BC here, we'll cancel with BC. Right, so BC cancels with BC, and we know that we're going to have sine A over A. What about here? AC is going to cancel with the A and the C here, so we'll have sine B over B. And here we have AB, we'll cancel with AB, and we have sine C over C. So that's what we're going to have. We finally have the statement of the sine rule, and the statement of the sine rule is that sine A over A is equal to sine B over B is equal to sine C over C. We may also write the sine rule in reciprocal. Remember a long time ago we stated that if two fractions are equal, if we invert them, they are still equal. So we may also have them in the inversed form. So let us see how this relates to our original triangle. Right. So A over sine A, what do we have? A over sine A, we know that A and A are opposite to each other. The same thing applies here for B. They are opposite to each other. And we have C's, and they are opposite to each other. No problem with that. Side A is opposite to angle A. Right. And so on. The sine rule can therefore be applied when a known side and a known angle are opposite to each other. So in any situation that you have your known side and this known angle are opposite to each other, that problem is a candidate for the sine rule. With the known side and angle forming one fraction of the equation, the side or angle sought after should be the only unknown in the equation that is used to find it. So if we're going to use the equation to find something, that thing that we are going to find has to be the only unknown in that equation. So we are going to be solving triangles by using the sine rule. So we're going to use the sine rule to solve a triangle. Right. Now the angle A is given, but its corresponding side is unknown. We have A is equal to 36, right? So we have the angle A is known, but the side A is not known. What about the B's? Both of them are known, no problem. Good. So the angle B and its relative are known. We have the side B and the angle B. The other side and angle are unknown. So, of course, C has no known relatives. There is only one angle missing. It is easy to find. The sum of angles in a triangle always give 180 degrees, so no problem finding that. It's as simple as this. 180 minus 36 minus 77, so we have what we call the rest of 80 degrees, that is 67 degrees. So we may now find either A or C. So let us find A first. It may only be found if we have the angle that is opposite to it. So if you are going to find A, we have to have the angle opposite to the side A. We're going to find the side A, we have to have the angle that is opposite to it. And of course, we have it right there. Of course, the problem cannot be solved if we do not have a side and an angle that are opposite to each other. So let us see if we have a side and angle opposite to each other. Right, B's. The B's are opposite to each other and they are knowns, so we can solve. We need to find A, so the fraction involving it should be included in the equation. So that is A. The fraction that contains the known side and the angle should also be involved. If we do not put in the known side and angle, we are going to be in a serious problem because we will not have any values to use to calculate our unknown. In this particular case, and is usually the case in trigonometry in general, mathematics in general, we cannot solve unless what we intend to find is the only unknown in the equation. So the other fraction must contain only known values. So the fraction that contains C and its associates are eliminated. The known values may be substituted in their respective places. So we have a formula and the known values are going to be inserted in their respective places. Of course, what do we know? A over sine 36 is equal to 2.5 over sine 77. We have the known opposite to each other, and of course they form one of the fractions. Of course, sine 36 and sine 77 are always known because you can just consult trigonometrical tables and also you can consult your scientific calculator and you'll get those answers. So let us transpose this. We need to find A. So what is going to happen? We have A over sine 36 is equal to 2.5 over sine 77. So we are going to transpose by multiplying by sine 36 on this side. There you go. So that is by transposition. Of course, we need to write down the values of sine 36 and sine 77. That we have done. And of course, when we have completed our calculation, A is equal to 1.5 meters. And it goes right there. So we need to find C now. Of course, we have to use the fraction that contains C if we are going to find C. And of course, we have to use a pair in the other fraction that contains two knowns. Of course, in this particular case, we have 36 degrees and 1.5 meters. We have 2.5 meters and 77 degrees. So we may use this pair or we may use that pair. But we are going to opt to use this because they are originals. So we're going to use the originals. So the fraction with A and A is going to be taken out. So that fraction is out. And our relationship is like that. Of course, we're going to substitute the values into the equation. All right, and we have that. Transposition as usual. This sine 67 is going to be transposed to the other side as multiplied, so it is going to be multiplied on that side. And of course, just find sine 67 and sine 77. Good. Complete your calculation and you have C is equal to 2.4 meters. Lovely. So the fraction that contains the unknown should be written first, preferably with the known in the numerator. This makes transposition simpler. By the time we get around to finding C, we would have two pairs of known sides and angles. However, we use the pair that we use first because we are familiar with its use. So we are familiar using the one that we had before, which is the pair of these, so we continue to use them. Of course, you remember how the sine rule is written? Sine A over A, sine B over B, or you may write A over sine A, B over sine B. Which one do we choose? We choose the one that gives the unknown in the numerator. That makes the transposition one step shorter. So let us now find the area of the triangle. Irrespective of the vertex that we are focusing on, we should get the same answer. So let us choose the vertex A. We are going to choose vertex A. What is the reason? Take note of the formula involved, the sides and the angle. We are using A because we have this one is already given and this is given. We did not calculate these. That is one reason why we are using the vertex A. Of course, the other side, which is 2.4 centimeters, is not very horrible. So our process should not be too tedious, especially in manipulating the digits. So the area is half BC sine A that we are going to be using. And of course, we do not have to use a formula because we know that the area is what? Half the product of two sides multiplied by sine of the angle that the two sides form on a vertex. So no problem with that. So we are going to just put in our sine 36, and of course all we do is multiply all of those figures, and our area turns out to be 1.77 meters squared. Sometimes problems are given in examinations that require the area of a strange looking triangle. Students most times get lost in all of the previous requirements of the problem and forget their half AB sine C. Students should make sure to remember this one while not forgetting the others. So while not forgetting all the other family, you need to remember half AB sine C for the area of a triangle. And more importantly, half the product of any two sides multiplied by sine of the angle that the two sides form. Here's another one. Solve the triangle with the following information and find its area. So A is 11 meters, C is 7 meters, and C is 22 degrees. A is not given, but its associate side, that is the angle A, is not given, but its associate side is given. B has no member, so there is no single member there for B. What about C? Right. So C, the family of C have their representatives, and we are going to say our aces in the problem are the uppercase C and the lowercase c. Those are our aces, meaning those are the most important things. So there we have our sine rule. And what do we say? Let us find A. That is the angle A. Its associated side is given. So the side that is associated with the angle A is given. Right, so no problem with that. However, we know that the other fraction must contain the side that is known, a side that is known, and an angle that is known. And they have to be opposite to each other, so we know that we are talking about 22 degrees and 7 meters. So let's put those in. So there you go. So B is going to be eliminated this time. And what do we have? Sine A over A is equal to sine C over C, and we are going to substitute the values. So substituting the values, we get sine A over 11 is equal to sine 22 over 7. And we may transpose, getting rid of this 11 that is divided on this side, multiplying on the other side. So there we have it. And of course, after that, we need to determine sine 22, and we put that right inside there. And all we need to do is do our calculation, and sine A is equal to 0.59. So how do we find the angle A? We have seen that if we have the sine of the angle and we need to find the angle, we may use what is called sine inverse. So A is equal to sine inverse of 0.59, and of course that is equal to 36 degrees. Good. Now that we have two angles, what do we do? So we have two angles, and the third may be found easily by using 180 minus 36 minus 22, and that is equal to 122 degrees. Now, let us in this problem, of course, the ACs we have declared here again to be the C's. Why? Because they are the known side. We have the known side here and the known angle here opposite to each other. So that is our key to finding anything that is missing while using the sine rule. So in order to find B, include its fraction. We are going to find B, so we're going to use this fraction. Of course, we are finding lowercase b. So we include its fraction, and we are including also the C's. Right. And the A's are out. Substituting the values, what do we get? Transposing. So we are going to transpose this sine 122 that we divide by here is going to be multiplied on the other side, and we have it there. And of course, B is equal to 15.4 meters. How do we get that? Of course, we have found sine 122 and sine 22, and we have completed the calculation in the background. When solving a triangle by using the sine rule, it is important to write the unknown in the numerator of the fraction and on the left-hand side of the equation. Although it is not desirable to use previously calculated values for reasons already discussed, in these situations, they cannot be left out all entirely. So we have to use previously calculated values in this because they are completely necessary. And of course, when applying the sine rule, put your unknown in the numerator on the left-hand side. That makes transposition a little bit shorter. So then, there's your reason for, in some cases, using sine A over A as opposed to A over sine A. We are trying to get the unknown in the numerator on the left-hand side. Now that we have finished solving the triangle, let us go ahead and find its area. So let us now find the area of the triangle. Using the sides A and C would be a most judicious move. They are already given, so we are sure that they are correct, and they come already rounded, so no fractions there. If we are going to use the sides 11 and 7, we need to also use the angle that those two sides form. Take note of the formula involving the sides and angle. Take good note of the formula that is being used. Area is equal to half AC sine B. That is what we are going to be using. And of course, it is not necessary to ask which side is A or C. Remember that the area pertains to the sides, two sides of a triangle, and of course that can be any two sides, but the angle must be the angle that those two sides form, and we are using it right here. So let us substitute the values in the formula. The sides A and C are 11 and 7, and of course the angle is 122 degrees. So we need to find sine 122 degrees. That's 0.85. And the area turns out to be 23.6 meters squared. The unknown should be in a fraction with a known. That is, its opposite should be known. The other fraction should have two knowns. This is an algebraic reason why known sides and angles are requirements of the application of Sine rule. The same requirement of one equation with one unknown should be maintained. Now we are going to be looking at the cosine rule, and the cosine rule comes in two versions, and we are going to call one cosine 1 and the other cosine 2. When applying the cosine rule, the convention of naming the sides and the angles are the same. So we are going to take a look at it again. So side A is opposite to angle A. Side B is opposite to angle B. And of course, side C is opposite to angle C. The derivation of the cosine rule is not a requirement at the C-sec level. Neither is the derivation of the sine rule, but I've decided to include the derivation of the sine rule in order that we can establish our formula for the area of the triangle. So cosine rule 1. The first version of the cosine rule is applied in a situation that has two sides of a triangle and the angle that the two sides form. It is used to find the side opposite to the angle. So we are going to find any side, say, but we need to focus on the angle that is opposite to the side that we are going to find. So let's see what this is saying to us. The two sides that form the angle are B and C. The angle A is the one that is formed by the sides B and C. The first occurrence of the sides in the formula are squares. We have two occurrences. So in the formula, the two sides that form the angle, they appear right there. And of course, they appear somewhere else. So they appear right here again. So the two sides that form the angle here, and they come here again. And of course, the angle that the two sides form will be this one here. So the angular representative of the vertex will also be in the formula. What do I mean by the angular representation of the vertex? Do not forget that the cosine rule is also defined on a vertex. That means if you want to find this side here, which is A, we are going to concentrate on this vertex that is opposite to A. So in the formula, the two sides that form the vertex are involved, and of course the angle that is at the vertex is also involved. There is definitely another pattern to consider. Remember that the formula for the area of a triangle derived during the presentation of the sine rule is defined on a vertex. The cosine rule is defined on the vertex that is opposite to the side that we are finding. Right? So there is no problem with that whatsoever. To find the side C, we use the opposite angle, which is the one that is the uppercase C, and the two sides forming it. So in order to find this C, we need to use the angle that is opposite to C and the two sides that form the angle. So we have there side A and B. And of course, they are right there in the formula. And right down there, you have them occurring again right here. Of course, C is the angle that is at the vertex. The angle C that the two sides form is also in the formula. It is opposite to the side C, which is lowercase c, that we are finding. Students should realize that a mathematical formula should be seen as more than a bunch of numbers and symbols. especially when it pertains to triangles that always have some simple pattern governing their manipulation. So when formulae are pertaining to sides and angles of a triangle, there must be a pattern that governs them. And the pattern is usually very simple. So let us look at C. With the pattern that we have established, light work should be made of writing down the formula for the length of side B. Of course, because this is B, so we're going to look at the vertex that is opposite to B, which is this one, and B is determined by using the two sides that form the angle and the angle that the two sides form. That's all there is to it. So the angle involved is B, and never forget that the cosine rule is defined on a vertex of a triangle. So we are going to have what? The two sides that form the angle. So we have a squared plus c squared minus 2 times a times c cosine of b. And it is as easy as that. Some students and teachers like to write the rule in a cycle that goes from A to B to C and back to A. Such a cycle will therefore cause C to come before A. And the formula that is used in order to find the side B is written as in the next statement. So it is usually written CA. So we have B squared is equal to C squared plus A squared minus 2CA cos B. Just to have it in a cyclic order, but it does not matter. Use cosine rule to find the unknown side in the following triangle. Can only use the cosine rule if you have the angle that is opposite to the side and also the two sides that form the angle. So no problem, we have that. The angle opposite to the side that we need to determine and the two sides that form that angle. So we have all the information that is pertaining to this vertex. The two sides and the angle. So without using the formula, we may just go straight ahead and determine the value of r. The missing side is r. The formula is defined on the vertex that is opposite to it. That vertex. Vertex with the two sides and the angle involved. And, of course, without using any formula, what do we write? R squared is equal to 9 squared plus 11 squared minus 2 times 9 times 11 cosine 60. No problem. No initial statement of the formula is required. Each item takes its place as if the formula were defined on those values. We simplify, and this is what we get. So R is equal to 10.1 centimeters. I hope that the presentation of this topic has liberated all students from the slavish adherence to a formula. Note that the formula was not quoted but applied. The cosine rule can be defined without any definite letter or symbols. The square of the sides that we need to find is shown by taking the sum of the squares of the other two sides and subtracting twice the product of the sides and the cosine of the angle that they form. That may just be a mouthful, but let us see if we can make some sense out of it. If we are going to find r, r squared is equal to the sum of the two sides, sum of the squares of the two sides that form the angle, minus the product of, minus twice the product of the two sides and cosine of the angle that the two sides form. So we're going to be doing that to another triangle. The missing side is Q. The formula is defined on the vertex that is opposite to it. That vertex with the two sides and the angle. And of course, no formula needed. 12 squared plus 8 squared minus 2 times 12 times 8 cosine of 132 degrees. And the values are inserted in their appropriate places. So the application of the formula is more important than its statement. And of course, after inserting the values, we simplify and that is what we get. How do we simplify? In this case, what do we notice? 132. Cosine of 132 is negative 0.67. So we multiply this by this. Negative multiplied by negative is positive. That will give a positive 64. Then 208 plus 64 is equal to 272. Then we need to find Q. This is Q squared. Finding Q, we find the square root of 272, which is 16.5 centimeters. The cosine of 132 is negative, as we'll find the cosine of all obtuse angles, and those values will be negative. This negative will multiply by the negative in the formula, and a positive result is obtained. Examiners sometimes catch students with one foot on the ground when obtuse angles are used. Students should, however, realize that whenever any obtuse angle is in a triangle, it has to be the largest angle. Because it is the largest angle, it is opposite to the longest side. Now, whenever we have an obtuse angle in a triangle, the sum of the other two angles must be less than 90 degrees. Also, the longest side of a triangle must be opposite to the largest angle. If it turns out to be smaller, so if we're working out a side that is opposite to an obtuse angle and it turns out to be smaller than any other side, then something is wrong. Usually it is wrong with this sign, but it's not limited to the sign. So it's usually the sign, but something else may be wrong. So when you have the side that is opposite to an obtuse angle being shorter than any other side in a triangle, then we know that something is wrong. Now we are going to be taking a look at the second version of the cosine rule. This version of the cosine rule is applied in a situation that has all sides of a triangle and no angle. It is used to find the angle opposite to the odd side. So, we may have a triangle with all of the sides given, but no angle, so we need to find an angle. And which angle it is used to find? The one that is opposite to the odd side. So why do we call it odd? Let's look and see why we call it odd. Cosine A is equal to b squared plus c squared minus a squared over 2bc. So what do we notice? We notice that b squared plus c squared is in the numerator. They are added, so they have something in common. Their signs are the same. Also, b and c appear in the denominator. Therefore, we are realizing from our experience now that b and c are closely related. A is therefore odd and is the odd one out. So A is the one that we call odd. So sides B and C that you see there form the desired angle. Those are the sides that form the desired angle. We need an expression for the angle A. It is the one formed by the two sides B and C. The first occurrence of the sides that form the angle are squares. And we have other occurrences also in the denominator. So notice how B and C seem to have something in common. Their squares are added in the numerator and they occur again in the denominator. So that is what they have in common. They have something in common. Notice also that we are trying to find this angle A. And of course, to find the angle A, we are using the two sides that form the angle A. The other side is opposite, that we have as the odd one out, is opposite to the angle A. So if we want to find, let's see if we can use a little pattern. To find cosine of A, what do we do? we square these for the two sides that form the angle, subtract the one that does not form the angle or is not a part of the angle, and then, of course, the two sides that form the angle are repeated here. B and C definitely have something in common. What can two sides in a triangle have in common? Only the fact that they form the angle in question. So the thing that they have in common is that they form the angle in question. So the two sides that you're going to add, and they are going to always occur again, like in the denominator, those sides are the ones that form the angle. To find the side C, we use its opposite, angle C, and the two sides that form it. So let us find the angle C. In order to find the angle C, we use what? In order to find the angle C, we are going to use the two sides that form the angle. What are the two sides? The two sides are A and B, and that is what we have there. The two sides are A and B that form the angle C. And of course, they are going to come again somewhere in the denominator. The two sides A and B are together in the numerator, having the same thing in common, which is they are accompanied by positive signs. They also make another show in the denominator. The side C is the odd one out. This is shown in the formula by its negative sign, while the others are positive. Its oddity can be seen in the diagram. It has no intimacy with the angle in question. So this is this side that we subtract. The one that we subtract has nothing to do with the angle in question. The ones that we add and are always together are the two sides that form the angle that we are trying to find. In the formula that is used to find an angle, the two sides that are always together are the ones that form the angle. The one that declares its difference is the one that is opposite to the angle. The third attempt can be successfully executed if we depend on the pattern instead of battling with the formula. So we're not going to be battling with the formula this time. And the angle that we're going to be finding is B. Remember that the sides that form the angle are always together, and the one opposite to the angle is the odd one out. No problem with that. We have A squared plus C squared, and then we are going to get minus the odd one out, which is the one that is not a part of the vertex, and that is over 2AC, and of course AC, as we have just said, are the two sides that form the angle. See how easy it is to write down the formula by which an angle of a triangle can be found, of course by using the cosine rule. Some of my students would say that there is nothing to it, and others will say that's all there is to it. Use the cosine rule to find the specified angle in the given triangle. Of course, there's only one angle there, A. So the specified angle is A. Use the pattern developed to write an expression to find the angle without exercising dependency on the formula. So no dependency expressed on the formula. Let's see how we may do that. If you're going to find A, the cosine of A is equal to what? The sum of the two sides that form the angle. Of course, the squares. So it's going to be 5 squared plus 8 squared. And we are going to subtract the square of the one that is out. The one that is out is 7 because it's not a part of the angle at all. So 5 squared plus 12 squared minus 7 squared, and over 2 times what? 2 times the sides, the product of the sides that form the angle. So we're going to go back with 5 and 8 again. So we have cosine of A is equal to 5 squared plus 8 squared minus 7 squared over 258, which is 2 times 5 times 8. Square, put the squares and we get those, and 2 times 5, 10 times 8 is 80. We have that. We put the squares here, and of course we are dividing by 80. And it turns out that we have 40 divided by 80. 40 divided by 80, 0.5. And we have cosine of A is 0.5. So we have the cosine of the angle. We need to find the angle. So we do the cosine inverse. And that is equal to 60 degrees. Do not forget about the inverse of a trig ratio. It is used to find the angle when the trig ratio is given. The angle that we need to find is A. The sides that form that angle are 5 centimeters and 8 centimeters. Those go together in the formula. Their sums are squared in the numerator and twice their product is present in the denominator. The side that view them with scorn, that is the one that takes away itself, is squared, and that is in the numerator. So the one that is subtracted is the one that is not a part of the vertex. Use the cosine rule to find the specified angle again, and that time the angle is B. And of course it's the same triangle that we are looking at. That one. So we know what to do. Cosine of B is going to be equal to what? Square the two sides that form the angle. 7 squared plus 8 squared. Subtract the one that is not a part of the angle. 5 squared over 2 times the product of the two sides that form the angle. It's as easy as that. So that's what we get. Square 8 we get 64, square 7 we get 49, and square 5 we get 25. What about 2 times 8 times 7? 8 sevens 56. 8 sevens 56, and we multiply that by 2. We multiply 56 by 2, we get 112. So cos B is equal to 0.79. So B is equal to cos inverse of 0.79, and that gives 30 degrees. So most students end up enjoying working with the cosine rule than the sine rule. I ask myself why. It's a little bit strange when the application of the sine rule is much simpler. I have figured out the answer. Students do not like to transpose. Because of this, they jump at every opportunity to apply the cosine rule that requires that students work on one side of the equation all the time. That is okay, as long as you do not force an application of the cosine rule where it is not applicable at all. Pythagoras' theorem and the cosine rule. So here we have a formula that expresses the cosine rule. I just could not end without declaring the close relationship between the cosine rule and Pythagoras' theorem. When the angle is 90 degrees, we have a right angle triangle. The cosine of 90 degrees is 0, and the term that contains the angle will therefore fall out of the formula. So let us see how it does that. So we have, if the angle is 90 degrees, so we are going to have cosine 90. Cosine 90 is 0, so 2bc times 0 is 0. So there's no term right there. So we're left with a squared is equal to b squared plus c squared. The triangle having a right angle becomes a right angle triangle. Remember that the side to be determined is opposite to the angle in question. The side that is opposite to the right angle is always the hypotenuse, the longest side. The formula fits Pythagoras' theorem perfectly, what we have just said. Remember that when we apply the cosine rule, the side that we are finding is opposite to the angle in question. See, we are finding side A, and we know that it is opposite to angle A. So, if we say cos A, say A is 90 degrees, then A squared is going to be the square of the hypotenuse, because the hypotenuse is opposite to the 90 degrees. So, the side is opposite to the angle, and this angle is 90 degrees. In a right angle triangle, the hypotenuse is opposite to the right angle. Therefore, A in this case would represent the hypotenuse. So the hypotenuse squared is equal to the sum of the squares of the two other sides. And we have a perfect example of Pythagoras' theorem.